Well, so thank you, Igor. It was a year ago that Igor asked me to speak here and assigned me the title, Supersymmetry and Superspace. And I never learned. I was so naive and dumb, I said yes, because it was a year away. But as the time came closer and closer, I got more and more worried because, well, it's a huge subject. And it's well known to some of you, and perhaps less well known to others of you. And it has a huge range of applications. And so I had to really think about what I would do for my 3 lectures at this workshop, at this school. And I decided that since I was the first lecturer, what I really should do is to try to set some of the groundwork down, some of the basics, and leave the exciting applications to the other lecturers and try to get us off on the same page. That, of course, means that some of you know much of what I'm going to say. On the other hand, I'm not sure that everybody knows everything I'm going to say. In fact, I'm not sure that anybody knows everything that I'm going to say, because some of it I made up just the other night myself as I was preparing the lectures. But most of the lectures are being taken from my book with Julius Wess, and I think that's appropriate because that book was born right here at the Institute many, many years ago when I was exactly in your shoes. But other parts are being also taken from the book by Buchbinder and Kusenko, and the book by Galperin, Ivanov, Ogievetsky, and Sokachev. Those are the 3 books that I use when I try to learn superspace. Unfortunately, they all have different conventions, so I can't guarantee that my lectures are internally consistent in their conventions from one line to the next. That's your job. I was supposed to assign homework. There's your job. Fix my lectures. The other thing is that these lectures are going to be sort of dry because they're really setting up the groundwork for the applications in the other lectures. And that's an approach I guess I learned from Julius Wess when we were writing the book, because I was an eager young student, and so I was trying to explain everything, and I wrote pages and pages and pages, and I gave him these pages, and he would cross all the words out. And I don't know if people who have looked at that book realize there are very few words in it. And that's a result of Julius crossing all my words out. But actually, in the end, he was right. Because the only reason that book has lasted close to 30 years is precisely because there are no words. The mathematics stays correct, and all the interpretation and the words change with the fads and the trends. So my lectures are going to be mostly formulas, not too many words. I'm going to leave it to the other lecturers to put the words in, and that's the deal. Is that okay? But feel free to ask questions, interrupt me if I'm making mistakes, come find me at breaks, lunchtime, whatever. I'm happy to answer questions. I'll do the best I can. Some of the material I know well, other pieces of it I don't know as well. And that might become clear also as we go along. So here's my outline of my lectures. Also tell me if I'm not writing big enough, if you can't read the dots and undots on the indices. So I'm going to start with some notation and conventions. In the lectures, I'm going to restrict myself to dimensions 4 and 5, and so the notation and conventions will apply to dimensions 4 and 5. I'm going to talk about the supersymmetry algebra and its representations. And here I'm going to restrict myself to n equals 0, n equals 1, and n equals 2. I'm going to move on and talk about fields and transformations. and in the process introduce the ideas of cosets and covariant derivatives. Both in general and then in their application to n equals 0, 1, and 2. And finally, I'm going to end with component Lagrangians. And that's it for today. So as you can tell, I'm going to move kind of fast, but I assume that you know much of what I'm going to be talking about already. Again, if I'm moving too fast, let me know. If I'm going too slowly, too bad. That's why I have the chalkboard. That's why I have the chalk. I'm doing that on purpose. Then the next 2 days, then I'll talk about n equals 1 superspace. I'm going to talk about n equals 2 in terms of n equals 1 superspace. And then I'm going to talk about n equals 2 superspace, where there's two versions, harmonic and projective. We'll see that things are well under control today. They're well under control for n equals 1 superspace, and things start getting hairier when we start talking about n equals 2 superspace. At the same time, n equals 2 superspace is also very closely related to 5 dimensions, and so I'll also talk about 5 dimensions. So that's the plan. So let me start with the notation in conventions. Well, as I said, I'm going to work in dimensions 4 and 5. That means I'm going to have coordinates, which I'm going to call xm and x5. And m is going to equal 0, 1, 2, 3, and then, of course, 5. And the metric I'm going to use is even this changes from book to book, and so it's a real mess to try to compare results. The first piece of notation is going to be spinors. And I'd like to talk about dimension 4 spinors, and then I'll talk about dimension 5. And we're going to exploit the fact for these spinors that SL2C, the group of 2 by 2 matrices, complex matrices of determinant 1, is the double cover of the Lorentz group. That means what I call a spinor, which I'll have a little Greek index alpha, will rotate under an SL2C transformation by a matrix, where the matrix is an element of SL2C. And since these are complex 2 spinors, and this is a complex matrix, I can also take as complex conjugate, and that will rotate the same way. Well, by the complex conjugated matrix, where the matrix M belongs to SL2C. The bars simply mean complex conjugate because you're unlikely to always see the dots. So this is the famous 2-component spinor notation. In my opinion, it's the only way to go. There's an invariant tensor. Which is the antisymmetric epsilon tensor, epsilon AB, and its complex conjugate, epsilon dot beta dot. And they allow you to form things like psi alpha beta, epsilon alpha beta. And that bilinear product is invariant under SL2C because it's an invariant tensor. Check it. And this works precisely because these are spinors. they anti-commute, and so the anti-symmetry of the epsilon is canceled by the anti-symmetry of the fact those are Grassmann numbers, and so it is a good invariant. Now, what does this have to do with the Lorentz group itself? We can let the sigmas, which I'm going to call sigma A alpha alpha dot, be a basis for 2 by 2 Hermitian matrices. And so I can write an object P alpha alpha dot, which is equal to P A sigma alpha alpha dot A. And so this is a Hermitian matrix. And therefore, under a Lorentz transformation, because it has a dotted and an undotted index, you can see that it transforms like this. Takes a Hermitian matrix to a Hermitian matrix, so that's good. This is a really lovely notation by writing vectors in terms of bispinors, and presumably that will be done in later lectures many times when one's dealing with twistor approaches to field theory and so forth. But I'm not going to talk about that here. The important point now is that the determinant of P is actually equal to P naught squared minus Pi squared. And so the determinant of P is the mass, the Lorentz invariant square of the P vector. And so the fact that the determinant of P is left invariant under SL2C transformations because the determinant of M is 1 is what tells you that this is actually a Lorentz transformation on the momenta itself. The sigma 0 is basically the identity, and the spatial sigmas are the Pauli matrices. Finally, I'm just roaring right along because this is just notation and it's not very interesting, but I want to get it down. So what I'd like to do is define an object called sigma bar, alpha dot alpha, which is raising the indices of a sigma matrix. And then I can make objects relations, and you can just check these yourself, that sigma A, sigma bar B, plus sigma B, sigma bar A, alpha beta is equal to minus 2 eta AB delta alpha beta, which is kind of reminiscent of the Clifford algebra that the gamma matrices obey for spinors. And I can create an object called sigma AB alpha beta, which is basically 1/4 sigma A sigma bar B minus sigma B sigma bar A alpha beta. So the symmetric combination of the sigma matrices gives the identity, and the anti-symmetric combination gives an anti-symmetric matrix, which is actually the generator of Lorentz transformations. Something that you can check is that epsilon A, B, C, D, sigma C, D is equal to minus 2I sigma A, B. So there's a duality to the sigma matrices. And what I'd like you to do, an exercise, is to use this and the sigma matrices to write a generator of Lorentz, which you all know is an anti-symmetric matrix, WAB. Write that matrix in terms of M. Mm-hmm. Right. That's too small. Everything else was big enough? So I have this thing called sigma AB. I'd like you to use that to write the generator of a Lorentz transformation, which is a real 4x4 anti-symmetric matrix. Not real, but it's a 4x4 anti-symmetric matrix. Real anti-symmetric matrix, right, in terms of the matrix M. it can be done, and you use relations like this. Okay. So the most useful thing you're going to learn in these lectures is the connection between these spinors and the commonly used spinors in textbooks. So let me define a Dirac spinor, which I'll say is a 4-component spinor. So this thing alpha hat runs over indices 1 through 4, and it's basically if alpha hat upstairs is equal to alpha upstairs and an alpha dot downstairs. And a Dirac spinor then is psi alpha chi bar alpha dot, composed of two component spinors. The bar of the Dirac spinor, psi bar Dirac alpha, is equal to chi alpha psi bar alpha dot. This notation is fantastic because it really emphasizes the fact that a Dirac spinor is built out of two-component spinors. It also makes it clear what a Majorana spinor is. A Majorana spinor, psi Majorana alpha dot, alpha hat, is equal to a self-conjugate spinor. It has one two-component spinor in it. A Weil spinor has one two-component spinor in it, and they're all the same. All these kind of spinors, Weil spinors, Dirac spinors, Majorana spinors, Pseudodirect spinors, are all just two-component spinors written in tortured ways. So anytime a neutrino physicist talks to you about Pseudodirect spinors, tell him to shut up and go away and learn about two-component spinors, because otherwise you get confused. The gamma matrices, the 4-dimensional gamma matrices, are just 0, sigma A, sigma bar A, 0. And if you want to go into 5 dimensions, the 5th gamma matrix, gamma 5, is equal to and we're done. That was incredibly fast, but it was just the notation. If you've never seen it before, you won't understand it by what I've done, but at least you have enough down that you can figure it out. If you've seen it before, it's a review, it sets the stage. The point I want to make is that two-component dotted and undotted spinors are the way to go. And I'm going to use them in my lectures for both 4 and 5-dimensional supersymmetry. Now I want to talk about algebra and representations. This algebra we're going to be talking about is the supersymmetry algebra, which is the algebra where the momenta commute. The Lorentz generators have the appropriate commutation relations to indicate that the form momentum is really a vector. That's what it means. And then MAB and MCD is a combination of things which obeys the right symmetry. I'm only going to write down the first term in the interest of spit time, and there are 4 terms. There are also anti-commutation relations for spinorial generators. basic rule is spinorial generators obey anti-commutation relations and spinor generators obey commutation relations. The two spinors anti-commute into a momentum. And there's spinors which say they have the appropriate commutation relation with the Lorentz generators. Several things to note. I equals 1 up to n. This means this is called n extended supersymmetry. N equals 0 is no supersymmetry at all. N equals 1 is ordinary supersymmetry. N equals 2 is the simplest extended supersymmetry. Those are the only cases I'm going to talk about in this lecture. The Q's transform in the fundamental of UN. That's an automorphism group of the algebra. The algebra respects those symmetries where the Q's transforming in the fundamental, the Q bars in the anti-fundamental. It's an automorphism group, and in supersymmetry, it's called the R symmetry group. The Z's have to be anti-symmetric because it's clear, because this is an anti-commutator, and if it's anti-symmetric here, it has to be anti-symmetric here. So the Z's commute with everything. They're known as central charges. In 4 dimensions with n equals 2, this is an anti-symmetric 2 by 2 object, one complex central charge. And it's very much consistent. They come from dimensional reduction from higher dimensions, as we'll talk about later. So I can't forget them when I put them down here. Anyway, we're interested in this algebra precisely because it's the most general set of symmetries of space-time that are consistent with the axioms of relativistic quantum field theory. Standard model, n equals 0, supersymmetry, n equals 1, 2, 3, 4, and so forth. Now, what we'd like to do is to represent this algebra on states in a relativistic quantum field theory. And so what we really need to do is to find the representations of this algebra. So there's a fancy theorem in mathematics, right? There's a theorem that says that there are no finite dimensional unitary representations of non-compact groups. And we want to represent symmetries on states in terms of unitary representations. And so you think, my gosh, what are we going to do about this? But this problem was solved years ago by Wigner in Princeton, and he did it in a beautiful and very physical way. And so that's the approach we're going to take. He basically introduced something called the method of induced representations. How does it work? It says, pick a preferred reference frame, classify the particles in that frame, and then just boost them into other frames, and you've got the whole story. Very physical. That's what we'd like to do. So in the method of induced representations, for massive states, how do you classify them? Go to their rest frame. And in the rest frame, states are classified by the mass of a particle and the spin. The spin is SU2, SO3. SO3 is contained in the Lorentz group SO31. So we classify them by their spin, which is SO3. And so in d dimensions, that means what you really do is classify states by their representation of SOD minus 1. This SOD minus 1 is called the little group. It's the group that leaves the particle in its rest frame. It just moves its spin all around. This is a compact group. It has finite dimensional representations. And so we just have a finite number of spins for this particle in its rest frame, and then you can boost it any way you want to get the full set, the full infinite dimensional representation. So how does that work then for regular? So we're going to make a table of the number of degrees of freedom. And we can have a scalar particle, we can have a spinor particle, we can have a vector particle. And in d equals 4, the little group is SO3. And a scalar particle is a singlet and has 1 degree of freedom. A spinor is a doublet of SU2 or a spinor of SO3. It has 2 degrees of freedom. And a vector particle is just a vector of SO3. In d equals 5, the little group is SO4, and SO4 is SU2 cross SU2. So now, instead of classifying according to spin SU2, you classify particles according to SO4 representations, SU2 cross SU2 representations. Again, a scalar particle has 1 degree of freedom because it doesn't rotate at all. A spinor particle, well, you need CPT and all that sort of stuff in a quantum field theory, and there's actually 4 degrees of freedom in a spinor. It's a 0, 2, plus a 2, 0 of the 2 SU2s. And a vector particle of SO4 just has 4, but in terms of SU2 cross SU2, it's the representation 2, 2. And so as we pass from 4 dimensions to 5 dimensions, we need to remember how many degrees of freedom are in each type of field, because we're going to be making supersymmetry theory. Supersymmetry balances Bose-Fermi, and we need to have the counting right. For massless particles, we can't go to the rest frame, so we have to do something else. So we pick a null vector, and classify by, well, not by the spin, but by the helicity, which is the group of rotations that leaves the null vector unchanged. So once you have a null vector pointing this way, what leaves the null vector unchanged? Well, you're already moving infinitely fast, so you can't boost along it. Rotating around it doesn't change it. So the only thing that changes it are the rotations that change its direction, and that is SOD minus 2. And so we can actually then make another table of the number of degrees of freedom in massless particles, and we'll look again at a scalar, a spinor, and a vector. But now in 4 dimensions, we're talking SO2, and a scalar particle still has 1 degree of freedom. A spinor actually has 2 degrees of freedom in a CPT invariant theory, because I have rotating that way and I have rotating the other way. So I have plus and minus helicity. And a vector also has 2 degrees of freedom because it has 2 helicities, plus and minus, left circular polarized, right circular polarized. Again, these are massless particles. In d equals 5, the little group is SO3. And again, a scalar has 1 degree of freedom. It doesn't rotate at all. A spinor still has 4 degrees of freedom. That's not the smallest representation of SO3, which is SU2. I think it must have something to do with the fact that we're trying to make a field theory where I have things like CPT symmetry. If somebody chooses to tell me why the answer is 4, I would be grateful, but it does. And a vector has 3 degrees of freedom because it's in the vector of SO3. Spinors are really tricky because as you change dimensions, the smallest irreducible spinor of the orthogonal groups have different conditions you can impose. In even dimensions, you can make them Weyl. In certain dimensions, you can make them Majorana. In other dimensions, you can make them Weyl and Majorana at the same time. And I know the answer is 4, but I'm not quite sure why. So now we know how many degrees of freedom are in the massive and the massless fields themselves. What now I would like to do is to represent the supersymmetry algebra. I'm only going to represent the supersymmetry algebra in 4 dimensions. We're going to do the 5 as we get there in the last lecture. So what we need to do is to look at the supersymmetry algebra in these various frames. So we want to look at the massive. And I want to look at in the rest frame. And in that frame, the Q alpha I and the Q bar alpha dot J becomes basically 2m delta alpha beta dot delta ij. And because we're in the rest frame, there's no difference between a dotted and an undotted index. And so basically this is a Clifford algebra with 2 times n generators. And I can use it to create and make particular states. So I start with a vacuum, which is omega, which is going to have spin j. And it is annihilated by A alpha I. Annihilates this for any value of j. And then I can build states on it by action with the creation operators A alpha I omega j. Now this is very tricky. This is spin j. This acts on it with a spin 1/2 object. So I get a spin j times spin j plus 1/2 and spin j minus 1/2. And if I have more than one, I have several such states. And then if I add to, again, A alpha beta I j dagger dagger omega j. I first I create this one, but I have to remember that I have these things anti-commute. And so you can build up the state representations that way. So how does that work? Let me write down the table that you get for the case of n equals 1 and n equals 2. For n equals 1, and this is massive, I can write down a table of states. And I can imagine, for example, that I start with a Clifford vacuum that has no spin, and I operate on it with, so I have if I have no index alpha I here. I have two of these that I operate on the vacuum with. Then I have two more that I operate on the vacuum with, but there are no indices here. And so it's antisymmetric here and here, which means the antisymmetric combination of two spinor indices is spin 0. And so I start with spin 0, I end with spin 0, so I have two states of spin 0. And here I hit on here, I get a single spinor of spin 1/2, 1, which has two states. And so I build up a representation that has two bosons, one Weil fermion, which has 2 degrees of freedom on shell, and so I have Bose-Fermi symmetry. I can also look at the Clifford vacuum, which has spin 1/2. There, what happens is I start with a state of spin 1/2. I act with this on it, which gives me a state of spin 0 and a state of spin 1. And then I act twice again, and I get a second one of these, and so I have two states of spin 1/2. So here is a representation that has two Weil fermions, 4 fermionic degrees of freedom, one boson, a massive vector which has 3 degrees of freedom, so 3 plus 1 is 4 equals 4. And so those are the n equals 1 massive multiplets. N equals 2 is a little trickier. So for n equals 2, I'm going to start with a Clifford vacuum of spin j. I'm going to act on it with A alpha I dagger on omega j. I'm going to act twice, A alpha I dagger, A beta j dagger on omega j. And then I have a term which has 3 A daggers, and I have a term which has 4 A daggers. So let's look at the spins. Let me first act on a Clifford vacuum which has spin 0. I start with one state of spin 0. I operate on it with this, which gives me 1, 2 states of spin 1/2. I operate on it with this. Now this I can symmetrize or anti-symmetrize in its spin index. If I anti-symmetrize in its spin index, I symmetrize in its isospin index. So that's 3 scalar degrees of freedom. I have anti-symmetrized in the spin index, which has 1, which is a singlet, and I symmetrize up here, which is a triplet. Or I can symmetrize down there and anti-symmetrize up here. Anti-symmetrizing up here says there's one such state. Symmetrizing in the spin index says it's spin 1. There's one state down here. And this state can be thought of as this state minus one of them. And there's 2 states worth of things that take away a state, which takes away a spin. And so there's 2 here. And so this is a state which has 5, 2, and 1. So immediately you see that n equals 2 without a central charge is, I guess I needed to put a sign up here. N equals 2 massive. No central charge. is not like n equals 1. Just simply having a massive spin 0 particle immediately tells me there's also a massive spin 1 particle. In the same multiplet. And the final thing I want to look at is n equals 2 massive with a central charge. No, I don't want to do that yet. I'm sorry. I have to come back to that. So now I want to look at n equals 1 massless. So for that, we need to pick a light-like vector like we did before and classify the states. We're going to pick a light-like vector that points in the 3 direction, in which case the anti-commutator of q alpha I q bar alpha dot j is equal to 4e 0, 0, 0 delta ij. And so this says the elements where the i's and j's are 2's anti-commute to 0, which tells me that the creation and annihilation operators are just 0. The only thing we have is a single creation operator that corresponds to the case where the i's alpha and the alpha dot are equal to 1. And what that does is it changes the helicity, and it squares to 0. And so the representations are hugely simple. And so I'm going to make a table for you. These are helicities. So if I start here with a state here, I hit it, I get a state here. I start with a state here, I hit it, I raise the helicity 1. You get the picture. Now we know that in a quantum field theory, if you have helicity minus a half, you also need helicity a half, and so these go together. And so you see there is a massless representation with 2 scalars and 1 Weyl fermion. There's a massless representation here with a vector and a Weyl fermion. And that's pretty interesting, because now we can look over here and compare it to the n equals 1 massive representations. There's a massive representation of n equals 1 with 2 scalars and a Weyl fermion. There's a massless representation with 2 scalars and a Weyl fermion. That just tells you in n equals 1, you can add mass supersymmetrically. There's a massive vector representation with 1 spin 0, 1 spin 1, and 2 spin a halves. Here I have a 1 spin 1, 2 spin a halves, 2 spin 0s up, but one of those is eaten to turn a massive vector. And so there's a supersymmetric version of the Higgs effect too. We can make the massive vector by eating 2 n equals 1 massless multiplets. Is that clear? In fact, that's so important, I'm going to write it down. The n equals 1 scalar multiplet can get a mass supersymmetrically. supersymmetrically. The n equals 1 vector multiplet can get a mass by eating an n equals 1 scalar multiplet. N equals 2. I'm going to ask you to do the exercise of working out the case of n equals 2 with no central charge. This is massless. And it excuse me. Acting on a Clifford vacuum with helicities. Here I get 1, 2, 1, 1, 2, 1, 1, 2, 1. These go together. And these go together. And as I said, times 2. Because we need a So for n equals 2, there is a multiplet which has 4 scalars and 2 Weil spinors. And there's a multiplet which has 2 scalars, 2 Weil spinors, and 1 vector. This is a massless multiplet. These n equals 2 multiplets break into n equals 1 multiplets. This multiplet is 2 scalar multiplets of n equals 1. This is a scalar plus a vector of n equals 1. Now let's look at how the Higgs effect works for the massive without central charge representation. Here I have a massive spin 1 particle. The massive spin 1 particle has to eat some sort of a scalar. If the massive spin 1 particle eats one of these multiplets, I have 1, 2, 3 scalar degrees of freedom. But I'm supposed to have 5 scalar degrees of freedom. And so what really has to happen is that I'm doing the counting wrong here. 1, 2, 3, 4, 5. Right. Well, I've got a couple of mistakes here. 2 plus 2 is 4 up here, first of all. That would help. Well, anyway, I'm having a hard time doing this in front of your eyes right now. But the point is, you take 2 so 2 of these and 2 of these make the 4 spinors. The 1 of these works, and then there should be 6 scalars in that multiplet somehow. Oh yeah, because it's doubled. Here we are. 1, 2, 3, 4, 5, 6. 6 scalars, one of which gets eaten to make this massive, leaving 5 scalars left over. And so you can see the super Higgs effect in n equals 2 is incredibly complicated. That's my bottom line. In fact, I've never seen anybody work it out. Does anybody, is it known how to do, I mean, has anybody seen it in field theory? I've never seen it. The vector has to eat 2 of these hypermultiplets. The other thing that's interesting also here is that in n equals 2, you can't just give a mass to the hypers without a central charge, because the massive multiplet has no spin, the massless multiplet has no spin 1, and the massive multiplet has a spin 1. And so this whole Higgs effect has to occur in order for the mass to be given. And the final thing I wanted to talk about was the case with a central charge, and then we'll stop looking at representations. So when there is a central charge, again, I'd like to look at the massive case. N equals 2. You can diagonalize to find there's some sort of creation operator. It's some linear combination of the Q's, which has M plus the central charge. And there's another linear combination which is M minus the central charge. And the first thing this tells you is that the central charge has to be less than the mass. Because if this right-hand side is negative and this left-hand side is positive, I can't realize the algebra. But the most interesting case is when the central charge is equal to the mass. Because when the central charge is equal to the mass, the b's are represented by 0, and instead of having 2 raising and lowering operators, we only have 1. And these are basically the short erupts of n equals 2 SUSY. And they have the same representations as massive n equals 1. And so this is trying to tell you that there is a tremendously important connection in n equals 2 supersymmetry between the central charge and the mass. Because all these problems that I had forming Higgs effects and so forth in n equals 2 without a central charge simplify beautifully when there is a central charge. Because the story for n equals 2 reduces to the story for n equals 1, because they're the same as the n equals 1 representations. And in fact, these play an important role. So the central charges play an essential role in the Kaluza-Klein reduction from, for example, 5 dimensions down to 4 dimensions. And they're exactly what allow all of the representation counting to work out beautifully, as we will see. So that little excursion was a bit more than I was bargaining for. It took a little longer than I thought, but I wanted to at least get down what the representations look like, because these are the states that we're going to try to realize now in terms of fields, and we're going to use these fields in the rest of the lectures. So we're going to look at 4 and 5 dimensions, n equals 1, n equals 2, the scalar multiplet of n equals 1, the vector multiplet of n equals 1, massive and massless, and the same thing in the case of n equals 2. Okay? And now we know what sort of degrees of freedom are contained in those multiplets, and we can work accordingly. So I'm a few minutes behind where I thought I would be. So we're not going to end exactly where I wanted to end today. But what I would like to do before I end is to go through an orgy of formalism on the subject of fields and transformations. I was hoping to end on a more positive note than that, but I'm going to run out of time. But what I'd like to do is to look at the structure of the algebra. Basically, we have some generators, which are the space-time translation generators. Where what I mean by P now, it's actually the regular P, as well as the supersymmetry Q's and the Q bars. When they're Q's and Q bars, these commutators are anti-commutators. But I have 2 Q's and a Q bar then goes into a P. The 2 P's go into a 0, and the P and the Q go into a 0. So I have a set of structure constants. But basically, I have a bunch of generators that obey something like that. And then I have the Lorentz generators, which basically say that M and P give some sort of a P, depending on whether it's a real P or a Q or a Q bar. And then I have M with M. And so we really are building up here is a beautiful coset structure where I'm on the top I have the super Poincarés, and in the bottom I have Lorentz generated by P's and M's and generated by M's. So the M's themselves close into a subgroup. Actually, the P's close among themselves too, so the coset itself is a group here, but right now I'm going to focus on its coset structure. And so typically what I have then is a full group G, and I'm going to identify points on G under the orbit of H, and then I have a section which is G mod H. And I am going to write a coset element omega, which is e to the I x dot p. And I'm going to identify things under right multiplication by h. So an element of the coset, a representative, is exponential of one of these generators, one of these space-time generators. I have a space-time coordinate for each such generator. And I'm identifying things under the right orbit of H. So I have a coordinate for each space-time generator. Now, under a group transformation, I'm going to act by a group transformation on the left, where omega is going to G omega. So that takes me from here. Well, in general, it will take me somewhere up here. and then I have to use it right H transformation to get back to my section. And so what I have is G goes to G omega, which I'm going to be defined as omega prime H. So G takes me from a place somewhere else where I've had to use an H transformation to get right back down. Does that make sense? In other words, omega prime, well, which is a function of coordinates x prime, is equal to G omega, which is a function of x times H inverse. This allows me to define a change of my coordinate from x to x prime. Now, when G is an element of H, I have that omega prime is equal to H omega H inverse. And that's very beautiful. And that gives me how x goes to x prime. It basically rotates the coordinates here by the adjoint action of the group H. And when G is an element, well, of the group now, G mod H, then I have omega prime is equal to G omega. Because actually, because the p's commute only into themselves, if I hit on the left with an exponential of p's on something that's an exponential of p's, I can rearrange it into just a new exponential of p's. And this gives me a motion of x to x prime as well. Now, what is a field? And I'm going to say that a field transforms as a finite matrix, as a matrix representation of H at the origin. In other words, H acting on the field at the origin is some representation of H acting on the field. Can't complain about that. I will define the field at the point X by a transformation, a translation of the field at the origin using the generators P. These generators take you from the origin out to the point P on my manifold. Now, how does that work then for a transformation of H? So, if I'm going to calculate what H is on phi of x, that is equal to H acting on e to the I p I x p phi of 0, which is equal to H e to the I p x p H inverse, H acting on phi of 0, which is equal to e to the I x prime p r of H phi of 0. But this p is an operator. These are just constants, some rotation matrices. They go right through each other. And so this then is equal to r of H phi of x. Good. X prime. And so this fancy formalism, which could be viewed as way overkill, actually is beautiful because it represents the transformation of H correctly. It has both the rotation of the indices of the field and the transformation of its coordinate. Similarly, I can calculate the G transformations of the same objects. let me operate with an element G acting on phi of x, where G now is an element of G mod H. Well, G acting on phi of x is equal to G omega phi of 0, where omega is the element that boosts me out to where I belong, which we've just decided was omega prime phi of 0, which was equal to, by definition, phi of x prime. And so this is done beautifully. Again, the translations in the coset take my fields and move their indices, move their locations from x to x prime. And the transformations in the subgroup, the stability group, rotate them according to the representation they are of H. Now, in my last 5 minutes, what I'm going to do is define some covariant derivatives and end on this feast of formalism. And I'm going to use these covariant derivatives tomorrow to make Lagrangians and get into superspace. So I would like to define the following objects. dA phi of x, which, well, is just dA omega phi of 0, where omega is equal to e to the I x dot p. I'd like to define something which I'm going to call dA left phi of x, and I'm going to define it to be I PA omega phi of 0. I'm going to define something called dA right phi of x, which is going to be equal to I omega PA phi of 0. And these are three different things because the p doesn't commute through the omega, nor is p d. They are very different things. In fact, d left looks to me like the generator, a translation generator, being applied to a field. That's what it says. In fact, so it's basically a group transformation. D right looks to me like it transforms the same way that the field does itself, because the field phi of x was equal to omega phi of 0. So under a group transformation, this thing transforms the same way as the field. That looks an awful lot like the covariant derivative. In fact, it is. And so we need those covariant derivatives if we're going to be making invariant Lagrangians under these transformations. This is an enormous pile of machinery, but it does, at the end of the day, simply get us where we want to go. So let me write dA left equals EA left M dm. In other words, I'm going to expand this thing in terms of something that looks like a Vierbein, a left Vierbein, and derivatives. And I'm going to write dA right equals EA right M dm as well. And then I can just compute these very simply. For example, dA left phi of 0, well, we just defined it to be EA left M dm omega phi of 0. But it's also equal to, by definition, IPA omega phi of 0. And if I compare this with this, I can strip off and find that dm omega is equal to the inverse of this matrix, omega. I can multiply on the right by the omega inverse, and I can turn the Vierbein around. I can write this as EMLA PAI is equal to dm omega omega inverse. Calculate d omega omega inverse, expand it out. There's a piece here that's proportional to these generators P. That is the left Vierbein. Do the same thing for the right Vierbein. I'm going to skip the steps, and we can conclude that EM right A, I P A is equal to omega inverse dm omega. You calculate it out, and you can compute. You can compute, for example, that dA left then and dB left is equal to minus I structure constants of A, B, C, dC acting on phi. I can compute then that dA right, dB right equals I F A B C dC right left, and you can compute that dA left dB right is equal to 0. I'm happy not to. I'm not going to show it now because we're late, but I will talk about that with anybody who wants to see it. The important point here is that the right derivatives obey the group algebra with one sign. The left derivatives obey the group algebra with the other sign, and they commute with each other. So in particular, that means that I've identified both the group transformation and a covariant derivative as advertised. So in my last line, I'm going to write down for you what that is, and then we're going to quit. I can write down a transformation of the field phi under the group as something like this. And I can write down a covariant derivative. And you can show then that the dA of delta phi is equal to delta of dA phi, precisely because the left and the right derivatives commute. This is a huge hammer that's not always needed, but it is very helpful when we're writing down supersymmetric theories in superspace, because we're going to have translation generators P that don't commute with each other. And so what we'd like to do is to write down covariant derivatives that commute with those supersymmetry translations. What I've done for you is identified a differential operator that implements a supersymmetry transformation, a symmetry transformation, and a differential operator that's a covariant derivative. So we have the tools that we need to write down invariant actions. And I'm going to stop here. Thank you.
There is time for a couple of questions now, and you can ask them without microphones. Just shout, speak up.
That's okay.